that. Anyhow, so let's get back to the question at hand. So we're summing up a bunch of e's, and the rule you've been told about is to use Leibniz, which just says, hey, whenever R allows equals for equals, then you can substitute equals for equals because you locally have access to R to make the justification of equals for equals. Okay, and so we're saying, you know what, under the constraint R, we know D is always going to be less than E. So we're going to use Leibniz to show that, hey, whenever I have E, I can massage that into some other expression, then I can split that other expression into two pieces, and then somehow I can probably get D out. Somebody's saying, wouldn't R already have been assumed if we are in the for any x satisfying R block? So right here, this is just a single assumption. This is just an atomic term. Right here is still an atomic term. Only right in here do we have access to a name called X that satisfies the property called R. So again, this is the idea of scoping. So only in the highlighted blue do we have access to X and R. That's all. I think this was this Alexandria talking. Sorry, I don't have anyone anyone showing me their stuff. So just quickly to show you the rules. This one we just proved a moment ago, right? Range weakening, and you can weaken the other way. Q and R implies R, right? If Q is less than or equal to R in the range, right? And now the one we're going to is a bit similar, but here's one that will be a bit useful. Whenever you have a sum, you can turn it into two quantifications, and whenever you have a sum, you can always add on an extra piece. This addition of an extra piece works because we're with the natural numbers, and when in the natural numbers, there's no negatives, so things can never get smaller when you add. They can only get bigger. Okay, so this might be a very useful thing to use in the follow-up, right here somewhere. Okay. Now, the hint says we're going to use cancellation of monas in the proof of the body monotonicity of some quantification inside another some quantification. And it needs to be discharged using the universally quantified assumption, which itself has a range predicate so that explicit implication of the corresponding Leibniz rule is required. Okay, and I hope people are comfortable with using orders on the side as we have before. So Lynn is asking about this question. Lynn, we only assumed this part, and now we're going to try to show this part. Okay, so we don't have access to anything yet. We start with the left-hand side, and we want to get to the right-hand side. We're starting with the greater side, and we want to go to the smaller side. Starting with the greater side, we're going to apply Leibniz, which says equals for equals. Because we have access to R, our assumption tells us D is less than or equal to E. And the hint is to use cancellation of monas. So we want to replace the expression like this. Right. So at the very end, instead of an E, we want to have like this. This one is D. Command Z, sorry. So this is the expression E we have up here, right? And it's supposed to be the bigger one, right? So right here we said E is the bigger one. So we'll replace every A with an E. And then the other smaller one is D. Okay. And then this rule that I showed you a moment ago, body monotonicity, says if one thing is always smaller than the other, then summing over the smallers is going to be less than or equal to summing over the largers. It says body monotonicity, and so we can apply that right here. Body monotonicity. Oh, okay. Body increasing for sigma. Okay. So now the only thing left to do is to finish this proof. So inside this proof, we need to show that E is the same thing as this thing. So let's put that in there. Okay. And the proof is done. Okay. There's just some theorems that need to be proved along the way. But the idea of this last piece was really to show you this line. This is the line that we wanted to show you. So there was a similar line on midterm 3, I think it was. And I just wanted to show you on midterm 3, we just gave it to you. I wasn't sure if it would be, if anyone would get it, so we just gave it to you on midterm 3. But the idea is using these multiple widths. So we've talked about it in lecture. I think you saw it in homework 8, and you saw it in midterm. And I just wanted to remind you, hey, sometimes you need to do multiple widths, and some people are still not comfortable with that. But you have seen multiple widths repeatedly already. This is not a new thing, but we just want to get you guys to be more comfortable with it. Marks will come out eventually. Marking is not really on the top of the priority list because you have access to CalcCheck. You know, if you have green, then you're doing well on the homework and on the midterm and on the assignment. If you're having less green, then you're not doing that well. So you have almost immediate feedback about how well you're doing. So getting back the actual numbers hasn't really been at the top of my priority list. Sorry. Trying to get lecture notes and homeworks and things out. All right. Was that who was that person who was talking? Was it Tammy? Was it Alexandria? Was it one or the other? I hope this answered your question. So so this is just wrap up from last week again, right? I really would like to get to a bit of induction today, so I won't spend too much time on these. I hope they're somewhat familiar by now. You definitely need to know instantiation. You used it for midterm 3, and so now just to not go too fast, you definitely need to know existence introduction for midterm 4, right? So we're not going to go too fast, and that's one of the things that you will need to know. And I've already written a bunch of exercises on using this. Hopefully we'll release it today. Maybe I'll call it midterm prep or something. Well, we shall see. I have to write midterm 4 too. Last time we talked about a theorem that said if you have for all xp, then that's the same thing as just having p, right? And that theorem was 916, and there's a similar theorem for existence. First, you do trading to bring r to the other side, and then if you have an existence that can, with an implication, that becomes a for all, right? That's all the way down here. And we said by 916, for alls can be popped off, and then you just get a naked theorem. So you've already seen these kind of naked theorems before that didn't have quantifiers on them. And now we just, this is the justification for them. These meta theorems justify how we were able to work with the substitution inference rule. So I just wanted to bring that again. We'll talk about 9:30 and how to actually use it maybe on Thursday. So we'll come back to it again.
Sorry, what is that line doing? The distributivity of or over for all.
This line is moving the parentheses. Is taking the 1, 2, 1, 2 distributivity of or. This or q is coming inside. Do you see it's inside the parentheses?
Oh, okay.
So in general, whenever an operation distributes over the other, times distributes over plus, then you have a times outside a quantification. You can bring the times inside the quantification. Okay, so you might have seen, if I multiply over a sum, I can get a sum of products. Okay.
I see. Okay, thank you.
You're welcome. So there's not that much new stuff, and that's why I'm going to go just a little bit fast. I just really want to get to a bit of induction. That's all. In the informal notes, in the lecture notes, I just wrote it in English for you. Provided x does not occur in P. In the book and in the slides, we will continue to use the notation introduced by the book. Negation occurs x comma q. But in the informal notes, I just wrote it out in English for you. Provided x does not occur here. So a few places I'll write something like that, where it's provided something does not occur somewhere. Okay, all right. So here's a way to actually use it. It's unfortunate that we're running a bit short on time, so I need to find out what we're gonna do. Okay. I'm glad you guys are asking questions. Please keep asking questions. Please do. I should get faster at answering your questions as you ask them. All right, so here's an example of how to use this meta theorem witness. So whenever you have an existence and it can give you a result Q, then really you can name that X, call it X hat, and then try to show Q. Okay, so for example, let's prove this implication, assuming we have this existence, right? So so A has an inverse, right? Called minus A, for example. Call that inverse alpha, and now we're saying the additive inverse of A is called alpha, right? That's what this equation says, and then we use that to prove things. Okay, it just means you actually have the name in scope. That's all this rule lets you. It says, you know what? If something exists, I really should have it. If there exists an X such that X plus A equals 0, I should have access to that X and I should be able to use it somehow. That's all this is telling you. It's saying if things exist, you should be able to use them. That sounds really reasonable, doesn't it? So that's all this is saying, and we'll show you how to do it in CalcCheck maybe Thursday. So that's all I wanted to show. That if things exist, you can use them to prove other stuff. Existence is that's a useful feature of this quantification. Summation doesn't let you do that. For all has instantiation, which is related but not the same. So that's a unique aspect of existence. If there exists an X with this property, then I can actually use X to make progress in proving other things. Okay, that's all we're trying to show here. Hopefully we can talk a little bit about induction before we wrap up. And then because I'm short on time, we'll have to talk more about induction next time as well. Okie dokes. All right. So are there any questions, concerns, or queries before I talk about induction kind of fastish?
Professor, sorry, it's me again. What's the deduction theorem? Like it says in what you just explained, it said Leibniz with 4.4 deduction theorem.
So deduction theorem, that's from chapter 4. The idea is that if you ever have P implies Q, you can just assume P is an axiom locally and then prove Q. And that's what the keyword assuming does essentially. When you're proving something, right? Whenever you say P implies Q, and you prove it by saying assuming P, and then you actually prove Q, the justification for making this proof using this syntax is the deduction theorem 4.4. So this is just a relaxed proof style. That's all it is.
So why does in the lecture slides, but it says like it's actually explicitly naming it.
Yes, it's named in the book as deduction theorem 4.4.
Oh, okay.
Yeah, so that is a name. We'll show you. That's why I said we'll show you how to do it in CalcCheck. Yeah. So okay. I don't expect you to be able to do it right now. I just wanted to show it to you, and hopefully we'll get to CalcCheck maybe next week. Sorry, maybe Thursday.
Okay, cool. Thank you so much.
So all of these meta theorems, it's the idea of the relaxed proof style, right? We're just trying to justify why you can do stuff like this to prove something like that. What's the justification? And we're just trying to show you, hey, the precise relationship between the two. That's all we're trying to do by showing you the meta theorems. They are in the book. We don't spend too much time on them because we don't want to distract people from actually using the resulting interface. Okie dokes. Man, I hope somebody says okie dokes, or I'm gonna have to drink more coffee.
Okie dokes.
Okie dokes.
No, so I saw on the feedback channel, people are like, this class is going too fast, and that's why I'm really taking, excessively asking, are you good? Are we good to move on? I want to make sure you guys really are comfortable, or at least kind of comfortable if you review the notes. I don't want to go too fast. Like it's there's a particular amount of content we do have to cover, but I do want to make sure you understand it. So, for example, this slide, natural numbers induction principle. Everyone should be comfortable with induction, so I won't review this particular slide. And of course, you always have access to the slides, but you definitely need to know what induction is by now, because you were tested on it back in midterm 2. Okay, so multiple ways to see induction. You may have seen it, as inference rules. Or as inference rules involving textual substitutions. You may have seen it in CalcCheck this way, and it may have phrased it this way as well. Okay. We showed you this by induction syntax back in week 2, I think, or week 3, just to get you actually being able to work with the interface with CalcCheck and proving things and not everything being so different. And back then we said, hey, you have to use by induction, but then we introduced this using keyword, right? We said using keyword, and so if you have induction as an axiom, which involves for alls, right? P is true at 0, and if P is true, then P is true at the successor of n, therefore P is true everywhere. Okay, so it involves quantifiers, so we can treat it as an axiom now, not some special rule. And so now you can say, I'm going to be using this axiom to prove this theorem, right? So we have that using syntax, which lets us use theorems as proof techniques. And so to prove this theorem, I'm going to use another theorem. And the induction on n axiom says, prove these two things, and you can have the last piece at the very end. To show P is true for every n, you need to show it for the base case, and for P, you get a successor of n. Okay. And so before we said, you know what, we said there was a base case and an inductive step. Well, here, because we're doing the using syntax, we'll just write the word subproof and then the other subproof. There's a subproof for the first argument and a subproof for the second argument. Okay. And then when you have access to them, you just prove them as you normally would, right? Notice, to get access to the induction hypothesis just becomes an assumption. A normal assumption, nothing strange, right? You're proving this for all, and the for all, you can start off with a for any, satisfying some assumption, and then you can just invoke the assumption, right? So induction, before it was a special thing and you had to learn it on its own, you can throw that away now. That's just trash. By induction is syntax that you can just throw away because you can use using, okay? So if you're like, oh, I want to be more comfortable with quantifiers, try to do some of the theorems you've seen with induction before. Instead of by induction, use using. Okay. And as always, you don't. This is really important to save you time. So I want to mention it before we run out. To save you time. Does somebody have questions? So to save you time on the midterm, I really want to emphasize this last part. When you're doing using, and you have subproofs, the subproofs will usually involve textual substitutions. Okay, do you see that right here? Textual substitutions. You don't have to write them down. You can just do them right away. So it's a subproof for 0 plus 0 and a subproof for right away. I've already done the substitution. Do you see that right here? I have to do the substitution. I have to do the substitution because the theorem says do a substitution. Do a substitution. I can just do them right at the top. Okay. Now to save you even more time, don't even write down the goal. Okay, don't even write down the goal, right? The subproof goal. This is super dangerous if you don't know what you're doing. So I labeled these V2, right? V1 and V0. Okay. So to actually use this last form, which will save you a lot of time, right? Induction says you need a base case and you need an inductive step. If to actually use V2, you really need to know how V0 worked. Okay. It will save you a lot of time, but if you don't know what's going on, I highly recommend you avoid doing this approach because you will confuse yourself. But to save you time on the midterm, you really do want to use this approach. You just write the word subproof and you're done, right? And then you begin writing your proof. Subproof, and then you begin writing your proof. But do you know what the subproof is? Do you know what you're proving? Right? So if you don't, you should write it down explicitly. And if you're still not sure what's going on, you should go back to version 0 and write everything down, including all the substitutions. Okay? So I can't stress how important it is to first get comfortable with doing things explicitly, every single detail. Right? It's a subproof for this thing with that substitution. And then if you're comfortable with it, then you can say it's a subproof, and I already did the substitution. And then finally, it's just a subproof. I know what I'm doing. I'm advanced. I'm not a noob. Life is easy. Get good, right? So.
Sorry, for the second subproof, like you use the for any syntax. Why not for the first subproof?
Because the first subproof. So this is why I said you need to actually know what you're doing to do this. The first subproof is not a for all. The first subproof, if you look at it back in V1, it's just 0 plus equals 0, right? Or if you look at it back in V0, it's just m plus 0 equals m, with m being 0, because that's what we're doing in the base case. There is no for all here. That's why we don't need a for any. There is no for all. So thank you to the person who just pointed that out. If you don't know what you're doing, you should write all of the subproof goal directly. Okay. And the reason we're switching to using the word using instead of by induction is because there's lots of inductively defined data types in computer science, like lists, strings, trees, and we want to show you a few more of those. And we don't want to give you a new by induction every time. So we want to show you how you just do using. That's all. Okay. And I've run out of time, so hopefully we'll come back to talking about induction in general tomorrow. I think these slides I've already posted them. Maybe they haven't already been posted. Anyhow, so I hope today was not too fast. I'm glad you guys asked questions. Let me see if there's any questions on the chat, because I only have one screen today. All right then. Thank you for coming to the lecture, and yeah, have a great day. And I'll be here for a moment or two if anyone has questions. Bye-bye.